You may have heard of graphene, the so-called wonder material set to revolutionize electronics. But it's difficult to scale up for industrial use. So scientists have been looking for alternatives that are easy to make, such as a new class of materials called metal organic frameworks, or MOFs. As the name suggests, they're made by combining two components, a metal and something called an organic chain. These can be used to create new materials with exciting properties. The problem is that scientists have not been able to introduce magnetic and electrical conductivity to metal organic frameworks, limiting their application in electronics. Until now. I'm Tamsin Bell, and I spoke with Kasper Petersen from the Technical University of Denmark to find out what they have been doing.
Our idea is to make materials in a new way. What we presented in this recent paper was concepts where we can actually introduce properties into metal organic frameworks. Like graphene, our material electrically conducts. But unlike graphene, our material is intrinsically magnetic. Graphene has been proposed as an integral part of future electronics, but its properties are not necessarily ideal for these applications. And from a chemical point of view, it's very difficult to tune those properties of graphene. Our types of materials and in metal organic frameworks in general, you can choose your building blocks as you like. So if you want to take a material and exchange half of the building blocks with something else, this is something you can do.
And how do you choose the different parts of the material that you want, so the metal and the organic part?
If you want to have a specific material with specific properties, you have to choose your building blocks quite wisely. You have to look at the building blocks individually and understand the energy levels before you put them together. Because in that way, you will be able to predict, can an electron travel from my metal ion to the organic part? Nearly all these existing MOFs, the energy levels are not matched, meaning an electron would not suddenly choose to jump from a metal ion onto the organic part of the material and onto the next metal ion and then travel through the material. But if you have done this wisely, this approach we have used is completely general and should open up many future applications. What makes them particularly interesting is that they are simple to synthesize and based on readily available precursors that you can buy, but still shows quite extraordinary physical properties.
Can you tell me a little bit about the composition and the chemistry of your material?
So this particular example contains a chromium metal ion, and then it contains an organic part that is a very simple small molecule called pyrazine. And what is interesting about pyrazine is it's one of the most common building blocks for metal organic frameworks. In fact, there are several thousand materials made with pyrazine. And actually, none of those materials are electrically conductive. So it's the property of the metal ion plus this particular ligand that makes this material electrically conductive. If I took other metal ions in the periodic table, it won't work because the energy levels are no longer matched.
What is novel about what you have done?
This concept about aligning the energy levels such that electrons can kind of move freely around in the material. So we can make designer materials in the lab for electronics. Secondly, our material is the first of such materials that is actually set up to be exfoliated. That means that you can peel off layers by layers of these materials in a graphene-like way. Then you have a material that is quite extraordinary because it's two-dimensional, magnetic, and electrically conductive. And until last year, actually, magnetism in two dimensions was a controversial topic.
What applications could your materials be used for?
This is really fundamental research, and this is the first example where we have shown we can make materials that have such interesting properties that we thought were reserved for traditional materials like graphene. That opens up a completely new field of tuning and tailoring properties. This kind of concept is not only reserved for electronics. This material here is two-dimensional in nature, but the concept that we used in this material could as well be applied in three dimensions to make highly porous material. Then you are on the way to, for instance, make very good electrocatalysts that are not based on precious metals.
How challenging would the scale-up of production of materials like this be?
Because this material is so simple, this can easily be done. a major goal now is to study how are the properties of these materials when it's sliced down to just one single layer of material.
That was Kasper Petersen from the Technical University of Denmark, and their recent results have been published in Nature Chemistry.